I touched on this briefly in our previous video, but one of the things that you can do is you can use an overall equation and you can look at a reaction mechanism to see, does this reaction mechanism produce the overall equation that it's referring to, in terms of, do the individual steps actually add up to the overall reaction? Does the rate determining step produce the rate law? And you can also look at, even in terms of energy, is the reaction overall exothermic or endothermic, and does the energy diagram actually show that when you're looking at the reaction mechanism and the curve? So let's look at, and really this is just easier to understand if we do some examples. So I think I've got 3 different examples here to show you. So in example 1, for the reaction 2A plus 2B makes 2AB, the rate law equals K times A times B, both first order. Again, not using the stoichiometry of the balanced equation to determine that. Okay, so part A says, using the 2 mechanisms below, determine which of the following proposed mechanisms is consistent with the overall reaction and with the rate law. Okay, so let's do that first. Okay, mechanism 1 has A and 2B in the fast step plus X, but then the slow step is just A times X. So first of all, does this mechanism produce our overall equation up here? The X cancels out because it's an intermediate. The 2 A's combine, so yes, it does produce the overall reaction. Does it produce the rate law, though? The rate law, remember, is A first order and B first order. And clearly the slow step is the rate determining step. It only has A as a reactant. So mechanism 1, yes, produces the overall reaction, but no, does not produce the rate law given. Okay, then in mechanism 2, again, we can kind of go through that. The X's are intermediates, the Y is intermediate. Then we've got 2 A's, 2 B's making 2 AB. So again, this mechanism also produces the reaction given above. Does it produce the rate law, though? Let's see. Our slow step would be rate equals K times X times B. But X is an intermediate, so we go up to the previous step like we've seen in our previous videos. And we can set the 2 sides equal to each other. Concentration of X equals concentration of A. So, of course, we replace that X in the equation with A. And what do you know? There's our rate law. That's the rate law they give up here. Absolutely, yes. Mechanism 2 produces the equation and produces the rate law given. Okay, and then in both mechanisms, is substance X an intermediate, catalyst neither or both? In both cases, X is produced and then used again. So that absolutely, just like Y in mechanism 2, is an intermediate. There are no catalysts in either of those mechanisms. Okay, another example. A new diatomic element, A2, is discovered and found to have a molar mass of 52 grams per mole. Okay, so that means that each A has a mass of 26, right? Because it's A2. I don't know if that matters or not. So at high temperatures, A2 reacts with N2 to produce the compound N2A, as shown in the equation below. This reaction occurs via a 2-step mechanism and has a delta H. Again, we'll discuss delta H more in Unit 5, but when delta H is less than 0, the energy, it's basically, that means it's exothermic. Okay, and if it's exothermic, we know that the energy of the products is less than the energy of the reactants. Okay, then they give us 4 different diagrams here, and clearly I did not make this. This is actually from an AP test. And then part A simply says, identify which of the diagrams shown above could represent this reaction. Justify your answer. So first of all, it's a 2-step mechanism. That's a big part of it. Okay, look at diagram 3. Diagram 3 has the first step, the second step, the third step. It's not a 3-step mechanism. 1, 2, 3. Each of those peaks, remember, this is breaking bonds in the first step, creating new bonds in the first step. Breaking bonds in the second step, or what we call the activation energy, right? That's the activation energy, is how much energy it would take to break those bonds. And then the energy released, and then the energy to break the bonds, and then the energy released. And this is, both of these are 3-step mechanisms. Okay, so it can't be 3. and it can't be 4. Okay, and then we come back. So it has to be diagram 1 or diagram 2. Again, 1 step, 2 step, 1 step. There's our second step. So, and because it's exothermic, we know that energy is released, and so the energy of the products is less than the energy of the reactants. Absolutely, the answer is diagram 2. Okay, and how would you justify that? You talk about how there's 2 peaks, so that represents a 2-step mechanism, and the energy of the products is less than the reactants, which means that delta H has to be negative. Okay, part B, using the diagram selected in part A, determine the activation energy of the first step of the reaction mechanism in kilojoules per mole. So the activation energy, again, is, and they're trying to trick you, so use the diagram selected in part A. So we're going to use diagram 2, okay, because they're putting all these dashed lines in there, 10, 35, 50, 75, that don't really mean much other than where are you starting? Where's, again, what you start at the energy of the reactant. So I'm starting right here, and I've got to go from here up to the top. So I'm starting at 45, and I'm going up to 75. Okay, that absolutely is the activation energy. Okay, 30 kilojoules per mole. Okay, and then part C, identify the rate determining step in the diagram selected in part A. Justify your choice. So what is the rate determining step? The rate determining step is the slow step. Okay, and what makes a slow step? The slow step usually is the activation energy. Okay, look here at diagram 1. Notice you've got this huge activation energy to overcome. And here you have this little cute activation energy to overcome. Absolutely, in diagram 1, the first step would be the slow step. Okay, so here again, you've got from 45 to 75, that's your activation energy. And then this activation energy is from, it looks like, what, 35 to 50. So that's only 15. Okay, so which of those steps is the slow step? Absolutely step number 1. And how would you justify that? Simply by saying, because it has the larger activation energy. Example 3, this is our last one here. C2H6O reacts with H2CrO4 as represented by the following equation. This reaction is known to be, again, exothermic. So if it's exothermic, remember the energy of the products is lower than the energy of the reactants. A proposed mechanism for the reaction is shown in the following table. So you've got step 1 is the fast step, step 2 is the slow step. The student draws the following energy diagram for the reaction. Give 2 reasons why the drawing is not consistent with the proposed mechanism, and then justify your answer. Okay, well, I think we just talked about that in the previous problem. First of all, the step that is the slow step is going to have the bigger activation energy. Again, they don't give us any numbers here, but roughly, what's the activation energy for step 1 is this, of course. And then what's the activation energy for step 2 is, again, you start at the bottom here and you just go up to here. So that activation energy, much, much smaller. So step 2 would be the fast step. Step 1 absolutely would be the slow step. Okay, and again, you could justify that really easily just by saying that step 1 should be the slow step because of the very high activation energy. Okay, so that's one reason. The second reason is it's exothermic. And if it's exothermic, again, the energy of the products has to be lower than the energy of the reactants. So again, how could you say that efficiently? You could say that it's not consistent because this graph represents an endothermic process because the energy of the product is greater than the energy of the reactants. And again, lots and lots of different ways you could say that. Okay? And so that is kind of our good little introduction there to our last 2 videos dealing with reaction mechanisms and using them to figure out the overall equation and which mechanism is the best one in terms of does it match the rate law and does it match the overall equation.